Hey everyone, how are you doing? Welcome to week 10 from Algebra 2B class, going over trigonometric functions. So, going through week 10, we are nearing the end of this course. We've been working our way through all sorts of trig stuff. This week it's kind of fun because we actually get into a lot of graphing and a lot of applying trigs. So we're going to be doing, here's our objectives. If I give you a sine or cosine function, I'm going to show how the values of the function itself come straight from the unit circle. And we talk about this idea of being periodic in nature. If I give you a sine or cosine function, we're going to show how we can take the function itself, take the graph, and then do some translations by changing the parameters. We're going to find key characteristics of the graph, including domain, range, amplitude, and translations. We're going to talk about frequency and period by also changing the equation. Then we're going to look a little bit at tangent functions. So we're going to use our Desmos calculator a lot today, looking at equations and graphs and just things that are periodic in nature. All right, so we're going to transition from the unit circle and triangles and see how it works in terms of coming up with a function to help start getting to where we're going into this transition. I've got a nice Desmos graph that shows you just how we get sine, cosine, and tangent as we build triangles around the unit circle. All right, here we are. What are we looking at right here? So we've got a unit circle. I've got a graph, x and y axis. This is the point 0, 0, right there in the origin. We see some pi's and pi over 2 and all that kind of stuff along here. We're getting to what that means. And what this is we're going to take our unit circle. I can adjust the angle. Let's make a 30 degrees right there. And what do we have? We have a triangle. There's our unit circle triangle with an angle of 30 degrees for reference angle. The radius is 1. So if you remember to our unit circle, the sine is the y value up and down. So at this point, there's my sine. And whoops, to get adjusted. And there is my cosine. I gotta tweak something here. Hold on a little bit. Yep, I changed my radius. Gotta make it back up to 1. There we go. Now what we're gonna do is we're gonna take our sine and cosine, and we're gonna plot these values over here. We're actually gonna draw our sine function based off this. So the sine is always your y value, it's up and down, the opposite part of the triangle, right? So there's my opposite in red, and I'm graphing that same opposite over here. So you can see as we go, start at 0, the sine is 0 on my unit circle at 0 degrees, and so at 0 degrees we plot that point on the sine function. If we go to 10 degrees, now it's going a little bit around the unit circle, so my sine is increasing, and so we can see from 0 degrees to 10 degrees, it increases a little bit. Let's go all the way up to 30. And now if you remember right, the sine of 30 is 1/2, right? Check out this point right here. We're getting at pi over 6. That's my radians. That's the same thing as 30 degrees. As a sine function of 0.5. That's the value of sine at pi over 6 radians. Let's keep going. Let's go to 45. 40, let me just type it in. 45 degrees. All right. Now 45 degrees. 45 degrees is the same as pi over 4. Whoops. I messed up my circle again. I got to make this locked somehow. I keep jacking up my radius, and if it's not at 1, it's going to change everything out. All right, so now the value, let me see if I can show that label. There we go. So now there's pi over 4. That's the same as 45 degrees. The sine of pi over 4 for my unit circle is the square root of 2 over 2. Well, that's about 0.707, so it's giving me that value of sine at that degrees. And look at it, it's connected it all right there. So we're drawing a function based off these values. Let's go up to 60. All right, there's 60 degrees. And a sine at 60. Whoops, that's not the one I want. How come that didn't move? I don't want to show that label. That must be the cosine one. Let's do, where's the sine one? There we go. There's the sine. I want to show that one. All right, so we're increasing. We made it up. The sine of pi over 3 is 0.866. That's the square root of 3 over 2. And let's go all the way up to 90 degrees. And the 90 degrees, the sine at 90 degrees, that's the same as the radians of pi over 2, is exactly 1. So look at what we got. We got a trig function when we connect all the points. The increasing sine value around the circle, we max out at 1. And let's keep going. If I keep going around, sine now starts to decrease. You can see the circle is decreasing. And what happens to my function? It decreases, and right at 180 degrees, sine is now 0. There is no y value. It's straight up at 0. And so the curve goes up, maxes out at 1, and then it decreases down to pi. All right, let's keep going along and along. What happens if I go past 180? Now we're getting to some negative values of sine, right? At negative 235, sine is going down. It's got a y value that's below 0, so it's a negative value. We lost our, what must not be exact. Let's go to 25. There we go. 5 pi over 4 radians is right there. That's a 45-degree reference angle right there. There's my negative 0.707. That's negative square root of 2 over 2 because we're going decreasing. Sine has a negative value in this quadrant. And so now my sine wave is going down. If I keep going all around, it maxes out at negative 1 right there, and then starts to increase around back to 0 right at 2 pi. This is what we call one full period. It's one whole lap around the circle, and it's one whole sine function. Starts at 0, increases, gets to 1, goes back to 0, goes to negative 1, and then back up to 0, all in the span of 0 to 2 pi radians. And guess what? We can keep going and going and going. This graph only goes to 360, but if I keep spinning around and around, I'll keep going up and down and giving this nice wavy pattern. So again, this is why we call them periodic functions. As we go around and around, we can see the function form over and over again, and it makes a nice wavy function. All right, cosine. Cosine is really similar, right? So let's go back. Let's take off the sine label. Let's show the cosine graph. So now cosine, notice at 0 degrees, it starts off, it's my x value, right? So if the radius is 1, it's a fully 1 unit away. And so it's starting at 0, 1. And what happens to cosine? As we go up, cosine gets smaller, right? The x value, this bottom part of the triangle shrinks. It starts at 1, then it gets smaller and smaller and smaller, and it shrinks in. And when we get up to 90, what's the same as pi over 2, cosine is all the way down. Now, I've still got the sine function, so you can kind of see how they relate. And they're really, really similar. But if I go around, cosine is now negative because we're on the left side and going to the left of 0, 0. And right at 180 degrees, cosine is negative 1. So right there, at a radians of pi, that's 180 degrees, my cosine value is negative 1 because it's negative 1 to the left of 0, 0. And now cosine will start decreasing again. It'll get to 0 right there at 3 pi over 2, or 270 degrees. And now cosine gets back positive. And so there you go. You can see how cosine in the red and sine in the blue are nearly almost the same exact function. They just start at different points. Cosine starts at 1, sine starts at 0. We can make cosine and sine turn into each other. We'll get into that later. But I just wanted to show you where these trig functions come from as we go around the unit circle around and around and around. We get this wavy pattern as we go on. Again, the x-axis here is your angle measurement. Traditionally, we do it in radians. and your y value is whatever the value of sine or cosine is at that specific radian. Okay, so we got cosine, sine. The only one left to do now is tangents. Let's play around with some tangent functions. That'll be kind of fun. So I'm going to take off sine so we don't see that one here. I'm going to turn on tangent. Whoop, we got a little sneak peek right there. Let's play around with what happens in tangent. So remember, tangent is the opposite side divided by the adjacent side. Well, when we do our unit circle, in my triangle, the opposite side is sine, the adjacent side is cosine. So tangent is really sine over cosine, and so it makes for some interesting things. When at 0, sine is 0 and cosine is 1, so tangent is 0 divided by 1, which is also 0. So tangent starts at 0, 0, just like sine does. Let's go to 45 degrees. Right there, 45, let me type it in. So at 45 degrees, let me see if I can put the coordinates here. Oh, I don't have it. Well, at 45 degrees, it goes all the way up to 1, because at 45 degrees, sine and cosine are the same thing. That's a half of a square right there. So the opposite divided by the adjacent side is the same ratio of 1. So tangent at 45 degrees is 1. And if I keep going up, 60, let's go all the way up to 90. And 90 gets weird because sine is at 1 at 90 degrees, but cosine is 0. And so 1 divided by 0 is undefined. What we're going to see is that it goes up and we have an asymptote at pi over 2, or 90 degrees, because tangent does not have a value. We can't divide by 0, and the cosine of 90 is 0. So anytime you have cosine of an angle and equals 0, we get an asymptote for our tangent function. Let's keep going. Oh, there's our asymptote, and now it jumped, and it's starting down negative again. So it's negative because cosine is negative. We go up, we go up, we go up. At 180 degrees, sine is 0, and so we got 0 for my tangent function. And as we continue increasing, both sine and cosine are negative right here, so now our tangent has positive values. And at 270 degrees, we get another asymptote because cosine is 0. You can't divide by 0. So you can see tangent, it looks much different than cosine or sine because we're dividing cosine divided by cosine. So anytime cosine of that angle is 0, we have an asymptote. At 45 degrees, or certain parts of 45 degrees for reference angle, tangent is either going to be 1 or negative 1. But there you go. You have now been introduced to sine, cosine, and tangent, and where they come from the unit circle. Let's go back and do a little bit more with the graph. So how do we use all these trig functions? If we have a function and it makes a nice wavy pattern, if we're graphing something that looks like this, when do we actually use a graph like that? Well, there are a lot of situations, there are a ton of situations that involve kind of cyclic patterns. One really big one is involving weather, right? Take a look at this graph. This is the daily average temperature for Columbus, Ohio. They gathered all the data from 1995 to 2015, and they plotted all these points, right? You can see that on January 1st, for all these 20 years, let's plot all the temperatures for those 20 years. So there's 20 points on January 1st, 20 points on January 15th, and they have all these points, right? Well, look at what these points seem to do here. They seem to form kind of a cyclic pattern, right? It makes sense. In January, the temperature's lower. It warms up. So as we get closer and closer to summer, we get a maximum temperature. It gets warm, right? Then we get closer to fall, and we get closer to winter, and things cool down. And so it decreases. But if we were to keep going, what would happen? It gets warm again, then cold again, then warm again, then cold again. That's a cyclic pattern, or what we call a periodic pattern. So we can use trig functions, which are waves, to model weather. It's pretty cool, huh? We can also use trig functions to model sound or any other type of thing that has waves. So magnetic waves, light waves, sound waves, anything that makes a wave can be modeled by a trig equation. So here we go. This is the graph. If you were to play middle C on a keyboard or some sort of instrument, again, different instruments would make slightly different graphs, but this is your middle C. It has a specific frequency to get that specific sound, and it involves a wavy pattern. I use an oscilloscope to help make this graph. So sound waves, we can use trig functions to show that wavy pattern to say this is what is happening with this specific sound. When you have noise canceling headphones, they use math, they use sound waves, and they figure out how to design your headphones so that it cancels out the sound. So instead of the wave going up making a sound, the cancellation figures out how to do the opposite so it negates the sound. So you're cutting out all the ambient sound because they're figuring out how to make an opposite wave so that they both kind of cancel each other out and you're not hearing any sound. Pretty interesting, huh? Just so you can see, let's actually pull out a digital oscilloscope. I'm going to use my little microphone here. So I've got a nice website for us to go to. Let's go to this website and I'll show you a little bit what I mean by sound waves. All right, here we are. We've got ourselves a nice little keyboard. Notice we've got it clicked on for sine right now. There's the volume. We can play it. We can adjust the frequency. I don't really know what these do, but we'll see. Let's play around with it. So I'm going to play a C. And we don't have anything show up. So let's kind of see if we can adjust some of these values here. There we go. Look at that. Okay, so this is involving being able to graph and see the pattern over time. Let's make it over 5 and see what happens. Oh yeah, so this adjusts how many waves we see at a time. So if I make it smaller, it's going to zoom in a little bit more. This is going to involve, I believe, how big the waves get. So let's adjust it to 1. And look at that. I don't know if you can hear, you can probably hear this sound, but when I play this sound, we get that particular wave. Let me play the same C, but up higher, and what do you notice? It's a higher sound, so it's a shorter frequency. It's got more waves in the same period. Less waves. If I go down lower, low notes are really big, fat, wide waves. So you can really get into the physics of music behind waves and certain frequencies and what notes go together and why they don't go together. But you have to have an understanding of trig and math to be able to handle sine waves and music and understanding all this stuff. So there you go. If you want this to play around with, if you're just bored and want to dink around on an oscilloscope, knock yourself out. I can give you this link. Okay, so you've got a nice introduction to trig functions, where they come from in our unit circle, and all the triangles going around and around and around. You've seen a little bit about how we can use trig functions to model things like weather and sound waves. Let's play around a little bit more with how we can make our trig functions fit certain data, how we can adjust it, make them taller, wider, slide around, make them match up, all by adjusting the function. So here we go, sine and cosine translations. This equation right here is what I want you to really become familiar with. We're going to play around with this on our Desmos calculator. But a lot of things we already kind of know, because when we get into functions, you change functions the same way, whether it's a radical function, an exponential function, a linear function, a quadratic function, even trig functions. We can still shift them up or down, right or left, make them get bigger or smaller, and reflect and all that good stuff. So here we go. Let's talk about some of these things here. Amplitude. This is a word that comes up in trig. And amplitude is talking about the value from the maximum point of the graph to the midline. So if you have a wave, kind of like this, right? Amplitude says, all right, let's draw a line from the middle and let's measure how far up my wave gets or how far down the wave gets, and that value is our value for A, the amplitude. So if you want to make your graph maximum or minimum get bigger or smaller, you change the value for A. Making A bigger will make your graph get taller, amplitude. If you make A smaller, it makes it smaller. Amplitude, it's sort of like turning the volume up. If you're any sort of musician and you have an amp for your guitar, all that is doing is it's taking your guitar's signal and you can turn it up or turn it down, make the volume louder or smaller by changing the amplitude. So if you're a musician, you're using trig and you didn't even know it. But amplitude is how big this value of our wave gets. We also have a horizontal shift and a vertical shift. So sometimes we want to move our graph to the right or left or up or down. The horizontal shift, if you remember horizontally, it's whatever you add or subtract to our x value. So if I want to shift right or left a certain amount of degrees or a certain amount of radians, I need to add or subtract to whatever is x. In trig, we often call that the phase shift, which is another term. If you're any sort of musician or if you play like electric guitar, you may have a phase shifter tool which adjusts and plays around with the type of sound coming out of your guitar. But that's what it's doing. Phase shift shifts our sound wave or a sine wave right or left. Vertical shift, up or down, is whatever we add to the function. So k is our vertical shift. And h is our horizontal shift. All right. So there we go. You're introduced to a couple things. Let's go ahead and just see how these work on our Desmos calculator. Okay, here we are. I've got my sine function. I've got my parameters, A, my amplitude, B, we're going to get into B eventually, H, my phase shift or horizontal shift, and K, my vertical shift. Notice I don't have any shifts going on right now. H and K are 0. My amplitude is 1, so this is just my basic sine function starting at 0, 0. If we increase at pi over 2 or 45 degrees, that's going to have a value of 1. All right, but what happens if I make my amplitude bigger? So I'm going to turn it up. Let's make my amplitude 2. And look at that. Now, instead of going up to just 1, now it goes up to 2 for my maximum. And it goes down to 2 for my maximum. If I make a 3, now it goes up 3, down 3, up 3, down 3. So we're making it even bigger. Notice it still goes from 0, 0. It still has a value of 0. It's still got the same period. So it goes a full, complete down and up, all in the span of 2 pi. There's my starts at 0 and it goes to 2 pi, and there's one full maximum and minimum. One full period happens in that 2 pi radians. That's one full lap around the circle. So there's my A. Let's go back to 1. My value for H shifts it right or left, right? So typically when H is 0, it starts at pi over 2. But let's shift it, I'm doing radians right here, so let's shift it pi over 4 radians. So pi divided by 4. And what did that do? Well, now instead of starting at 0, 0, we shifted it to the right, because it's x minus h. We shifted it to the right pi over 4 radians, which is the same as shifting it 45 degrees. So we are starting at a different place. It still has a maximum of 1. It decreases and does all the same stuff, but now it just got moved over a little bit. So it's starting at a different value. And you may have noticed, let's actually do this here. I'm going to graph cosine. So it's g of x equals cosine of x. And what's funny about sine is if we do enough of a phase shift, let's actually go backwards. We can make the sine function and we can shift it So I took my sine and we shifted it left by 90 degrees, or pi over 2. So right here it's starting at 0, 0. But notice how it compares to my cosine graph. The sine and cosine are now exactly the same because we shifted sine 90 degrees, so now it matches up in value exactly with cosine. Keep this in mind. In the future weeks, you're going to see that we can make sine turn into cosine by doing certain phase shifts or doing certain horizontal shifts. It's a good property of trig functions. Sine and cosine are the same thing, just with different horizontal translations. All right, so there's shifting it right or left. Let's go back to 0. And ultimately, if I shift it up or down, we can just add or subtract a k. So you can see that right there. All right, so how is k useful? Well, if we're modeling something like weather, let's play around with the weather, right? So we have 12 months. So I'm going to say, all right, let's go for x-axis. We're going to start at 0 and go to 12. We're going to go step by 1. So there's 12 months. On average, we may say, on average, let's make it bigger. It's going to go up to possibly 90 degrees in the summer. So we're going to make a maximum y value of 90, but it gets down to an average of 30 degrees in the winter. We're going to go up by steps. So we're going to make a trig function that seems to fit the weather. So notice we can't see our function yet. We need to make it increase. So if it goes up to 90 and down to 30, that means on average, for the whole year, our midline, k needs to be right at 60 degrees. So there you go. We're starting at 60. It gets hotter, it gets colder, it gets hotter, it's colder. But now we need to make it line up. In January is the coldest month. Well, let's actually make it white. So we need to be able to get up to 30 degrees. So if it's at 60, and the weather gets up to 90, but then down to 30, that's an amplitude of 30. So let's change this to 30. And we got to zoom out a little bit. But there you go. So the weather has a high temperature of 90 degrees, but a low temperature of down to 30 degrees. And there's January, February, March. We're going to do our 12 months on here. So we'll adjust the window a little bit more. But we're trying to make a function to model the weather. So now I need my low month to be right here at January, because January gets the coldest. So we need to shift things to the right a little bit. I'm going to shift it right there. So if we shifted it 2.6, now my low month is lining up with January. It warms up February. And then number 3 is March. So March it warms up, but it's still not quite there, right? This is saying it gets cold, hot, all within like 3 seasons, 1 year. So I need to stretch and make it wider. This is where B comes in. B affects your period. So if I make B smaller, it's going to make it wider. If I make B bigger, it squeezes more waves into that time period. So B is what we call affecting the frequency. So I want to make it from January. I want one full period to start low, get high right in the middle, and then get low again. So I'm going to shrink it. And that's pretty close, but now my low is not at 1, so I need to move it over to the right a little bit. All right, they're starting the low. This is the coldest on the first month, which is January. It's warming up. January, February, March, April, May, June, July. The 7th month would be the hottest. Oh, it's almost lined up pretty good. And then what we need to do is have the coldest month be back down here. This should be right at 13. So my period is not, just a little bit too wide. So let's make it 0.51, 0.52, 0.53. That's pretty darn good now. Yeah, look at that. So there is a nice modeling of the weather. My low point on January, it warms up for February, March. Right here on the 7th month, it gets up to 90 degrees and starts to cool back down as we get to September. And then back here on 13th, that's the same as the 1st. So now we got one whole revolution. Back on January, it gets cold again. Now it's not quite exact, but if we had all the weather data plotted, it would kind of fit a season like this, right? So this is how we can adjust all the parameters to start using math to fit the data that we have. And this would be a reasonable model for graphing weather data. We had to adjust the amplitude to affect for high temperatures and low temperatures. We had to set the vertical shift to get kind of that mid baseline temperature, and average is 60 all year. We had to adjust H to get a shifting, so it started on the right value that we wanted to start with, and shifted right or left. We had to affect B because we wanted one whole period to span over 12 months. So we multiplied it almost by half, a little bit over half, to get it stretch over from 1 to 13 for that 12-month period. And there we go. It's not too bad, right? Let's go back and look a little bit more at our functions. So let's do a problem together here. We want to write a sine function for this particular graph. So I've got a wave going on. Let's write a sine function, and then we'll write a cosine function. So how do we go about doing that? Well, remember, we need to figure out things like amplitude, horizontal shift, vertical shift, etc. So if I'm looking at this one, it looks like it goes up to 2, has a maximum value at 2, but then it has a minimum value of 0. So my amplitude A, it goes up 1, it goes down 1, it goes up 1. So the value for A is just still 1. There's no amplitude on this one. All right, so that's easy. For a sine function, sine is supposed to start at 0. So this has a shift, right? Instead of starting at 0 right here, it's starting, well, it went over a little bit, right? So we have some sort of value to shift it over, that is shifted over to the right, so we need to affect that. And if it starts at 0, it was also shifted up. Looks like it was shifted up 1 unit. So my value for K, looks like we added 1, so moved the whole graph up 1. So my middle line is right at 1. And then if we shift it from 0 to about pi, just a smidge over pi, in fact, we'll just call it pi. We'll call it average pi. So it shifted to the right pi units. So what I'm going to do here is for my phase shift, I'm going to have x minus pi. So let's put it all together in a sine function now. So this function should be f of x equals, my value for a is 1. So 1 times sine of, we had a phase shift of pi units to the right, so we have my degrees minus the phase shift of pi units. It was a little bit over pi units, but we're just going to call it pi for this example. And then we shifted it up 1 unit. If I graph this one, this is going to be pretty darn close to how this graph shows up. I might make this one a little bit bigger. Pi is about 3.14. I might say, you know, a little bit more than pi. Let's make it 3.3. So we could tweak this one to get it to match up. But there's a pretty reasonable graph based on, equation based on this graph. So there's a sine function. Let's write a cosine function. Let me switch colors here. So cosine, if you remember, starts at the maximum. So we still have, for cosine, we still have the same amplitude. We still have the same vertical shift up. But cosine starts at the maximum value here. When x is 0, it should start at the maximum, but instead it's been shifted to the right. Pi, let's see, 1, 2, 3, there's pi. That's pi over 2. Pi over 3 pi over 2 is right there, and it's a little bit past 3 pi over 2. So let's see, so we might say even What would be it? So 3 over 2 would be the same as 6 over 4. Let's just say a little bit more. Let's say it's 7 pi over 4. That's a little bit more than 6 pi over 4. So let's say it has a phase shift of 7 pi over 4 to the right. That's how many radians. So the cosine, if I wanted to make the same graph but cosine, we would have my function is equal to 1 times the cosine, and cosine starts at a different place, so we had a different phase shift. So it was x minus 7 pi over 4 plus 1. All right, hopefully that gives you an idea of how we can take a graph and fit a sine or cosine function to what we're seeing on the graph. We'll do a couple more of these as well too. How would I write a trig function to represent this graph? What's going on here? Well, let's find my maximum minimums. So it looks like it's maxing out right here at a value of 1, all right? But my minimum is down here at -5. So from 1 to -5, that's a complete value of 6. That's 6 apart from the maximum and minimum. Well, if it's 6 apart from high to low, the halfway point needs to be right here at -2, which means the amplitude is 3. It goes up 3, back to 0, then down 3, then back to 0, and up 3. So my amplitude is 3 for this function. We're going to do a sine function. So sine always starts, before we get into the vertical star, let's get the shift. We already got the shift going down. Instead of centering around 0, we already got the vertical shift. It went down -2, right? That's the halfway point along the middle. So my vertical shift, I got to go down -2 units. All right. Now, let's play around with horizontal shift. Remember, sine function should start at 0, 0. So this point right here, if there was no shift, would be right here at x value of 0. So one way I could do it is say, all right, well, it was shifted to the left, and now we got to figure out, this is pi over 2, this would be pi over 4, so 1 pi over 4, or 2, I could think about it in eighths, pi over 8, 2 pi over 8, 3 pi over 8. I'm going to say this shifted over 3 pi over units 8 into the left, so we need to have a value for h be -3 pi over 8 units. And again, I just did some fraction work. So there's pi, so each line here represents pi over 4, so halfway in between pi over 4 has to be an eighth, so that's 3/8 pi. All right, let's put this all together then. So my function here, we have an amplitude of 3, goes up 3, down 3. It's a sine function. We based it off sine, so starting at 0, 0. It shifted to the left 3 pi over 8 units, so we're going to have x plus 3 pi over 8. And we had a vertical shift down of 2 units, so we need a -2 at the end. If I can check this, go to my Desmos calculator and graph it, it would look just like that function right there. Okay, how do we do some stuff with negatives? So we can turn any cosine function into a sine function. We already kind of showed you this with the right phase shift. We can also turn any sine or cosine function into the positive trig function with the right phase shift as well. So I want to show you some stuff here on the Desmos calculator. Again, being aware of how negatives affect things. So let's play around with sine and cosine and trying to get them to look the same. All right, here we are. We've got, right now we're graphing just the sine function itself. Again, they're starting at 0, 0, going up 1, down 1, up 1, down 1. And you can see wavy patterns. It repeats every 2 pi. Okay. Let's graph, if I put a negative in front, what is this going to do? So let me just take off this phase shift right now. If I make my amplitude negative, that's going to be the opposite. Instead of going up, it's the opposite. So it's going to go down. It looks kind of cool, but there's the opposite of negative sine of x. Now, I can think about a phase shift in the fact that if we make it the opposite, if it repeats every 2 pi, watch what happens when I phase shift it by 180 degrees or by pi. I just made it look exactly the same. This blue graph and red graph, even though it's a negative sine function, we shifted it so it matches right back up and is not the opposite anymore. So we shifted it by 180 degrees, and now sine of x is the same as negative sine of x plus pi. So we can put a phase shifting in to match up. Cosine, we already seen how we can make cosine also match up. Check that out. So even if I have a cosine, if we shift it by 90 degrees, so we had x minus pi over 2, that makes it match up with sine. Same graph. And finally, cosine, I can put a negative in cosine, but if I shift it instead of negative 90 degrees, I can shift it the positive 90 degrees, or pi over 2, and it still looks the same. So that gives you an idea of how phase shifts and how applying negatives can really make sine and cosine become really the same graph. All 4 of these are the exact same function, just with different phase shifts to move it right or left to match up, or a negative to kind of do the opposite, starting to kind of make it go up instead of down or down instead of up. But again, finding that connection between sine and cosine and realizing they're the same thing, just different horizontal shifts or different ways to open up, is a good idea to keep it back in your mind. Okay, the last big idea is this idea of period and frequency. Period, when we talk about period with trig functions, period is how long it takes for one complete wave to happen. The frequency is how many wave cycles happen in 2 pi. So that's saying, okay, as one lap around the circle, 2 pi, how many waves up and down happen? Period is how long is just one wave. So let's take a look at this one. So here we go. This first graph starts at 0. We have a complete up and down and then back at 0, all in the span of 4 pi. So with this first graph, number 1, the period would be 4 pi. That's how long it takes for one complete wave to happen. So that's graph number 1. That's totally messy. So period 1, the period equals 4 pi. Now the frequency is how many wave cycles happen in 2 pi. Well, if we go from 0 to 2 pi, we see we have half of a wave. So for the first graph, the frequency is 0.5. The half of a wave in that 2 pi span. Okay, let's look at the other graph. It's a little bit different, it's a little bit more wavier. So let's go from the period, how long for one complete wave? So it starts here, up, down, up, and there is one complete wave cycle. So the period for this graph is just pi. It takes pi, or 180 degrees, for one full wave. So we're kind of shrinking it in a little bit. Now the frequency is how many wave cycles happen in 2 pi. So from 0 to 2 pi, we get 1, 2. We get 2 wave cycles. All right, so what do we have with that? So we know the period. The frequency, how much it happens, is just equal to 2 pi, which is one full lap around the circle, divided by whatever the period is. So there's a relationship between frequency and period. Here the period was 4 pi. So if we did 2 pi divided by 4 pi for the period, we saw the frequency is 0.5. If the period was pi, we did 2 pi divided by pi. The pi's divide out, we see the frequency is 2. So this relationship between frequency and period is a helpful one to understand and to work through as you're analyzing working with trig functions. Okay, let's write an equation for this graph right here. What do we got going on? We're going to put it all together. We've got, let's do a sine function. First of all, we see it's going up 3 and then down 3. 3 to negative 3 and then back up to 3. So my amplitude, A, is 3. From 3 to negative 3, halfway in between that is 0. So there is no phase shift. So, no vertical shift. So I'm not going up or down at all. If it's a sine function, we need to start right in the middle. So right here is the starting point, but it should be right here. So we shifted it to the right a little bit. So I need to figure out, well, how much is that? So right here is pi over 2. Right there is pi over 4. Right there is pi over 8. And wow, it's such a tiny little bit amount over there. Tell you what, I'm going to go over with this one right here. This is a nice starting place. And it kind of lines up on this line. So there's pi over 2. Let's see. Pi over 2. Pi. So this would be 3 pi over 2 right here. So we shifted it to the right. Pi over 2. Actually, sorry, this would be 3/4 pi. 1/4 pi, 2/4 pi, 3/4 pi to the right. That's how far we shifted. So my horizontal shift is 3 pi over 4. Okay, but now we need to get in this idea of period. How often does it repeat itself, right? Let me put a different color here. Let's go black. So we need to look at one full frequency and try and figure out how often it happens. So if I'm starting here and I go all the way to 2 pi, it looks like we, in that span of 2 pi right here, it ends right there. So how many waves is that? It's 1, 2, 3, 4, 5, 6 waves. So the frequency is 6. All right, so 6 complete waves happen in 2 pi, which means the period, which means one wave is 2 pi, which is one full period. But we have 6 of them happen, so we need to divide by 6. So the period in this case is just pi over 3. All right, so the frequency was 6. The period is pi over 3. So what we would do in terms of multiplying it out then is we would, in our parameter for b, we would multiply it by 6 to have it happen 6 times as often. So how do we put all this together in our sine function now? So f of x equals our amplitude of 3. It's a sine function. We've had a frequency of 6, so I got to multiply it by 6. So it happens 6 times more often. But we also have a phase shift, so we shifted it to the right, 3 pi over 4. So we have x minus 3 pi over 4. Notice I have to have that inside a parenthesis, so the 6 affects the x, but you just have to have it separated out. If I don't have it, then it's sort of like it distributed the 6 over to the shift, and it kind of messes things up that way. So there we go. So we keep it separate, our horizontal shift separate from our frequency. And finally, I don't need to add or subtract anything for k because we didn't shift it up or down. So there you go. There we graphed it just like this. So now let's actually just check this one and just make sure. So again, it started at -3. And we had ended at 2 pi, and we had 6 of them. So let's see if this one actually works out. We'll check it by our own graph. All right, here we are. So I got my blank graph. I'm going to graph the one we just made and see if it actually fits. We had 3 times sine of 6 times x minus 3 pi divided by 4. And it's looking a little bit crazy, right? Because we have a lot of waves. So let me expand things out a little bit and make it fit. So for the x-axis, let's only go from negative 2 pi to 2 pi. And from my y-axis, let's go from negative 4 to 4. Okay, so we're starting at negative 3, which is good. We're going up to positive 3, which is also good. Now, in the span of 2 pi, so here's 2 pi right here, does it repeat 6 times? Well, there's 1, 2, 3, 4, 5, 6 times, just like we wanted. So 6 waves all happen in that 2 pi period right there. And it's exactly like on the graph that we wanted to do. So I'm feeling pretty good. I'm checking my work. I like this. This equation works. All right, I wanted to touch a little bit on tangent just at the end. Remember, tangent was kind of weird. It had all those vertical asymptotes because a lot of times you sine divided by cosine, and cosine equals 0 at points. So when we do it, here's our general form for tangent function. You have all the same things here, a, b, h, k. You can shift it to the right. You can shift it up or down. You can change the frequency, how many times it occurs in 2 pi. And you can get into amplitude. So on this particular one, let's take a look. So it's starting at 0. What is the period of this basic tan function right here? This is y equals tangent of x. So it starts, goes up, there's my vertical asymptote, and right here, it repeats. It starts to repeat again, goes up, asymptote, again repeats. So when I look at the tangent function, the period, how long for one wave? The period equals pi. It's different than sine or cosine. For sine and cosine, we do one whole wave in 2 pi, and then we can shrink it from there. But with just the basic tangent function, it repeats every pi unit. The amplitude, you can't really think about amplitude as much, but if you do make it bigger, you'll see tangent increase faster depending on whatever you make it for the amplitude. But in this case, it doesn't have a maximum or minimum, so I can't really think about amplitude, but it's still affected by my value for A right there. My vertical shift, I can still shift it up or down. Notice right here, it seems to start at 0, it curves up, and then right here, what we call reflection point, or it changes from kind of increasing, and it kind of curves the other way that way. So that's for value of k. If you find this 0 point, you can tell if it's been shifted up or down. But anyways, you can play around with this on your Desmos calculator as well and just kind of get used to what the tangent function looks like. The big one is you just want to be aware of asymptotes whenever cosine equals 0, because you can't divide by 0. All right, so with this function, what would this function look like? Well, there's no vertical shift because there's nothing being added at the end. There's no horizontal shift because there's nothing being added or subtracted x. So I do know it's going to go through the point 0, 0. This 2 over here is going to make it squish in, so it's going to go twice as fast. So the period, instead of being pi, the period is going to be pi divided by 2. So if it goes up, that means we have an asymptote at pi over 4, and it's going to kind of go like that. And just go like that, and then right here, kind of the same thing. And then it goes up like that again. And so you get there, from 0 to pi, there's now 2 full cycles of the tangent function. And we could keep going and making it, but that's what that 2 does to it. So it's twice as many waves. Now what does this -5 do? I actually should have waited on that one, but the negative is going to make it open the opposite, and it's going to grow a lot faster. So instead of starting at 0, 0 and going up like this, it's going to do the opposite. It's actually going to come in and look more something like this, as if I graph it. So the negative in front, we have a negative amplitude. It goes in the opposite direction. So again, those are just some things opposite. Those are some things to kind of look out for as you're working with trig functions. Look out for negatives, things affecting the period, any shifts. And you should have a good idea what you're doing. We can come over and graph this as well on our Desmos calculator as a way to check too. So let's go ahead and do that. All right, and here we are. This is what it looks like. So the -5, it's not even really, it's growing really fast, right? If it was -1, then it would look a little more curvy, but with the 5, it's increasing and decreasing really fast and almost kind of straightening out. But it still starts at 0, 0 because there's no vertical or horizontal shifts. Instead of happening one time within pi, it happens twice in pi. So there's 1 period, 2 full periods within this pi cycle. So that's what the 2 is doing. If I take away the 2, now there's only half as many waves. If I add the 2 back in, it's making the frequency happen twice as fast. If I made it, want to get really crazy, I could even make it like 6. Look at that. There's now 6 waves happening in that full period of pi cycle. Okay, so hopefully you feel like you have a good grasp of sine, cosine, and tangent, where they come from in the unit circle, how to change the parameters of your function, the amplitude, the horizontal and vertical shifts, the period, a lot of this vocabulary, but you know how to make your graph look like what you want to do. We even did that graph where we did kind of an imaginary weather graph over 12 months, where we had to change the period, had to change the shift, to do all that kind of stuff. Hopefully you get a good idea with graphs. Again, use your Desmos calculator a lot. And let me know if you have any questions this week as you're working on all our assignments. Have a great day. I'll talk to you guys later.